Hey y'all, so I wanted to do some last minute practice problems. So this one video is just osmosis and osmolarity, osmotic pressure. So first, let's go over what it is by practicing number 8. This is a biology question, but it can help understand chemistry. So albumin is the major blood osmoregulatory protein. So albumin is something that's in the blood, kind of like a solute. Um, what effect would a sharp rise in albumin solute in the blood have? So these are some vessels of blood filled with blood. And then we have this much in our first condition. Then it says there's a sharp rise. So let's imagine many more of these. So in the second condition, people who are familiar with osmosis would know that more water is going to go into the blood vessel in the second condition. So that's all osmotic pressure is. Osmotic pressure is the pressure which, oh my goodness, my cat's crazy, y'all. Which solutes have. So which solutes can attract water with. So you know how water can push and it has a pushing force. That's what osmotic pressure is. It's the pressure of the water pushing into the blood vessels. Or if you want to think about it differently, it's the sucking pressure which solute has for water. So solute causes the water to be pulled in. All right, that's all it is. It's the force of the water into the blood vessels. Let me move my kitty. Okay. So in that case, which one of these would be the answer? What effect would it have? A drop in blood pressure? No, because there's more fluid inside the vessel. So that would make pressure go up inside the vessel. An influx of interstitial fluid into the bloodstream? Yeah, that makes sense because this is the interstitium, right? Up here, interstitium, however you spell it. An efflux of fluid out of the bloodstream and into the interstitial fluid. So that would be like stuff coming out, like water or fluid leaving the blood vessel. So we know that's not going to happen. So just B, that's the definition. So now let's do the actual math calculation. So it says, what is the osmotic pressure of a solution prepared by adding 13.65 grams of sucrose to enough water to make 250 mils of a solution at 25 degrees Celsius? Cool, so we have all the information we need to solve this equation. This equation solves for osmotic pressure. It's pi equal I MRT. So we can define everything here. The pi is just a symbol for osmotic pressure. That's what we're solving for. We want to know how is the pressure increased when we add more solute, because we know solute attracts water. And Van Hoff factor. So Van Hoff factor is just a factor that measures solubility of something. So here we have sugar. Sugar is not soluble in water, which means it's not like salt, for example, which is going to turn into Na plus Cl. It's just going to stay itself. So since it stays itself, sugar does not divide. Its Van Hoff factor is 1. If it were to divide like salt into 2 pieces, then it'd be 2. Van Hoff factors can be 3, 4, but usually they're 2 or 3. And they can obviously be 1 in cases like sugar, which are not ionic. Okay, so we have our Van Hoff factor. Now let's find our molarity. So good thing it gave us the volume. Do this cat. Please go over here. Okay, so we want to find the volume, the molarity, the moles per liter. So let's do that. We have 13.65 grams of sugar He's so cute. Oh, the screen changed. Okay, so we have 13.65 grams of sugar. And I bet by this point you guys have all solved it yourselves. And enough water to make 250 milliliters of solution, 25 degrees Celsius, and sugar. Okay, so we have to convert to moles here. So let's find the moles, because we're looking for moles per liter and it gave us only 13.65 grams. So we're going to use the molecular weight to find the number of moles, because the molecular weight given on the periodic table is equal to 1 mole of a substance. So 342 grams equals 1 mole. You can use that. Just do a quick calculation. All right, that's like 0.04 moles. And it's gonna be over the liters. We're gonna bring these and put them under. So this is 0.25 liters. So when I put these over each other in my calculator, I get 0.16 as my molarity. Okay, so we're gonna put that as our molarity. And let me just erase this and write the whole equation front and center. So far we have 1 for Van Hoff factor, Ri, then our molarity is 0.16. Then lastly, R is a constant, so you just have to memorize this. It's 0.0806. So there's lots of different R's in this class, so just be aware which ones are necessary. The units for this are liters times ATM over moles times K. So you can see here, this has liters over moles over liters. For molarity, that's the units of it. And Van Hoff factor has no units. So the moles per liter is going to cancel out with liters per mole, because here's the liters canceling out up and bottom and moles and moles. And then the last thing we want to be left is pressure, right? Because we're solving for the pressure of the fluid when it pushes through like a membrane or something in order to get to some solute or any type of through any type of liquid. So what we have to do is cancel out the temperature. So that means our temperature must therefore be in Kelvin. So let's just convert 25 degrees to Kelvin by adding 273.15. And that's it. You will solve for osmotic pressure like that. I'll let you guys do the calculations. All right, that's it for this video.